Hi everyone, I'm Richard, a postdoc at UCLA, and this is Design Space Exploration for Board-Level Circuits, or more generally, exploring alternatives in component-based design. Printed circuit boards, or PCBs, are at the heart of almost all electronics, including interactive devices, and provide capabilities not available in simpler prototyping techniques like breadboarding. And even if you're not a board designer, the ideas to design space exploration do apply more broadly. PCBs are designed with software tools. For the circuit design portion which this work addresses, this is generally schematic capture, where users draw the circuit graphically using components like this resistor and LED. But even to build this LED circuit, one needs to know the circuit structure, the resistance calculation, and part selection. This can be a substantial barrier to entry for novices who may want to build customized devices. Recent work, particularly in the HCI community, investigates electronics design tools that better support novices. One broad approach is synthesis, where the tool generates a circuit from a specification. It can be a partial circuit, like this USB connector and LED, which the tool completes by inserting a microcontroller and power supply. Yet, the drawback of automation is the inability for the user to make fine-grained choices based on their expertise or specialized requirements. For example here, if they wanted a different power converter. The other broad approach is high-level design, where users work with high-level blocks like microcontrollers instead of raw components like chips. This abstracts away electrical engineering details while still leaving important choices in the user's hands. Yet, this still requires users understanding how to map ideas down to blocks and the trade-offs between choices. Towards an ideal design tool, we can look at desirable characteristics from the creativity support tools literature. In their analogy of this mythical, unaffordable thing called a house, the ideal one is both low floor, or easy to get started with, and high ceiling, or capable for experts. Here, schematics would be high floor and high ceiling, synthesis tools are low floor but low ceiling, and high-level design tools are mid-floor and high ceiling. One approach might be to bridge the best of synthesis and high-level design. And fundamentally, synthesis searches over a design space of valid designs, but returns just one. But the tool doesn't necessarily have to make that choice. Instead, we can present the user with options and trade-offs. For example here, plotting all possible voltage regulator choices. And this is the idea of design space exploration. While this has been explored more in other domains like mechanical engineering, applications to circuit design outside the beginner-focused tool have been limited. So, towards the goal of better electronic design tools for everyone, we seek to answer some of those questions in this work, like how this can scale from novices to experts, and what design abstractions are suitable for exploration. In particular, we build a prototype design space exploration tool for board-level circuits. Then, we run an exploratory user study to understand how this functionality is used in practice, with a focus on driving future work. We'll describe our system through an example design, a USB-powered blinky LED. Architecturally, this has a USB port for power, a microcontroller that runs code controlling the LED, and the LED itself. A voltage regulator adapts voltages for compatibility. The high-level design tool that we build on, which we presented a few years back, contains a library of these blocks. These blocks contain logic to generate down to a schematic level circuit, for example here, calculating the resistor value. These blocks are also part of a type system defining interchangeable parts, and a design can also contain abstract blocks that stand in for all subtypes. For example, this voltage regulator is abstract. Instead of naming a specific part, it is a generic three-ported block that any compatible regulator can be substituted into. The choices have different trade-offs. For example, linear regulators are simpler, buck converters are more efficient, while boost converters are invalid here. Ultimately, instead of defining one specific design, these choices encode a design space. As there isn't an objective best choice, we leave it open to the user. The actual tool is part of an IDE since the underlying design system is a hardware description language. However, the design space exploration subsystem is purely graphical, so feel free to ignore the code. Here is the example design. To search over voltage regulators, we start by adding it to the design space. Then, we add objective functions of interest, here component area and current draw. Now, we can start the design space sweep, which compiles all 21 options and completes in about 30 seconds. While we have a results table by default, we can also configure the scatter plot, here visualizing size and power consumption. In the feasible space of black points, we can see a trade-off between efficiency and size. The plot also shows abstract and infeasible points in brown and red respectively, for context. If we prioritize efficiency and choose this point, we can commit the choice, which inserts the corresponding code. The design can then be compiled and the result imported into a board layout tool. In this second scenario, we're interested in a combinational search across microcontrollers and voltage regulators. We start with the design modified with an abstract microcontroller. Similarly, we add both the microcontroller and voltage regulator to the search space. We can also add objective functions, including component area, current draw, and price. Then, we start the sweep process across the much larger space of all combinations. This completes in about 2 minutes. With many objective functions, we switch to parallel coordinate plots, which allow simultaneously plotting of multiple axes. Here, we plot the regulator, current draw, price, area, and microcontroller. All the axes are parallel, with a polyline per design through its points. From this mess, we can select to incrementally filter, first choosing the ESP32 microcontroller. From the plot, we can see that these designs are relatively large and power hungry, as their points are near the top of both axes. We can further filter by current by selecting this lowest current cluster of points, then zoom in to the area axis and select the smallest point. With a single point, we can again commit the choice and get to a board. Architecturally, our system consists of design space definitions, objective functions, plots, and the sweep itself. There's more than shown in the example, but it's all in our paper. With this prototype tool, we can use it to understand more about how designers might use design space exploration in a realistic setting to ground further development of tools. As such, we ran a qualitative user study. The study started with a guided tutorial through the earlier example, followed by a project making use of design space exploration, and ended with a semi-structured interview. Participants averaged almost 3 hours on projects and 2 hours on interviews. Since our tool is designed to scale from novices to experts, we recruited 6 participants with a range of experience levels. As we believe our tool most benefits low intermediate users like makers, they make up most of our participants. 2 more skilled users rounds out the data. To maximize realism, participants determined their projects subject to limitations of our design system and libraries. Participants had a wide variety of projects, including internet-connected sensors and interactive devices. These generally followed the tutorial's architecture with the USB port, voltage regulator, and microcontroller. Most participants conducted searches across regulators and/or microcontrollers to find compatible parts. Sometimes, they brought their own knowledge to the table. For example, here, choosing the NRF52 for its energy efficiency. As an example of a design flow, Participant 5, a novice, was interested in mechanical keyboards. Participant 5 started with a 5x15 switch matrix, but this was beyond the I/O capability of the default microcontroller. Participant 5 initially tried reducing the switch matrix size, but on our suggestion instead did a design space sweep to find a chip with more pins. Though just one flow, it highlights trends common across many flows. One is the importance of the validity indicator, which helps even novices build correct boards with minimal knowledge. Yet, this design space exploration interface still required users to know where the search is useful and what to search over. We do note that our user study is more exploratory and intended to generate ideas for continued work. Future studies could focus in and be more evaluative with more participants. Still, one takeaway from our prototype and user study is that design space exploration can scale well up and down the complexity and experience spectrum. It provides support to help novices towards an electrically valid design while being flexible enough to allow experts to bring their knowledge. Yet, as a prototype system, the specific user interface and interactions need refinement, especially to support novices. Future work might examine how to seamlessly recommend searches to users with an invalid design. Finally, our goal is to build useful electronics design tools for a wide audience. However, our library-based approach depends on community contributions to really work. Design space exploration may be a compelling feature that helps bootstrap this process. And on that note, if you're interested, this is all open source, and I would love to have users and contributors. Otherwise, in summary, we've presented a design space exploration tool for electronics design and exploratory user results. Building upon prior work that implicitly encodes a design space, we can sweep and visualize alternatives given a high-level design. This can both help novices get to a working design while not constraining experts with more specialized requirements. We hope that this is another step towards powerful tools that are both low floor and high ceiling.